All right, good afternoon. Let's continue where we stopped off from last class, which was the summary of findings. So, any questions about anything so far? Okay, questions answered. Then let's move on. We're going to look at the derivations for REQ and then talk a little bit more about sources, voltage sources, current sources, as well as power and energy as relates to these sources. Okay. So we know that if we have a large resistive network and we connect it to a single source, uh, the single source does not recognize how many components are connected at its terminals. You could have one resistor connected. It's simply supplying its current and voltage, depending on the settings, to that one resistor. If we add a second resistor between the pair of terminals to the voltage source, it still sees only one. But now that total resistance that is being seen by the source is the total equivalent resistance. And so we call that REQ. In a series circuit, you've already studied this in the past, REQ is simply the sum of those resistors. And for parallel networks is the reciprocal of the reciprocal sums, or the sum of the reciprocals. So again, the takeaway point is, the main point is that if you have a network or a circuit that comprises of multiple resistors connected in every configuration, series, parallel, T, Y, or neither series nor parallel, it appears as if it's one single resistor between any two pair of terminals. And so we call that REQ, total equivalent resistance. Okay, sometimes it's some authors, some books like to use RT for total or just RTOT. So it's total equivalent resistance between those two pairs of terminals. Okay. Now, this is important to remember. If you have a circuit like, if you have a resistive circuit like this that comprises the multiple resistors, there are multiple nodes in that circuit, right? The total single resistance is different between any two pairs of nodes. So if this network, for instance, let's say this circuit or this network has 5 nodes, A, B, C, D, E. The total equivalent resistance between any two nodes is never the same. Okay, it's always different depending on the configuration. So REQ between any two nodes or any 2 points is never the same. It depends on the circuit connections, or more appropriately, it depends on the resistive connections, on how those resistors are connected to each other. Okay. If you measure between A and B, it will be some value. If you measure between B and C, it may be a different value depending on how the circuit is configured. Okay. All right. Now the importance for REQ is this. If you have a source and you're connecting multiple loads to that circuit, and we need to know how much power or how much energy is required from that source, it helps if we can model the entire load or all the multiple loads as one single load. Okay. And because we can model it as one single load, as one single resistance, it still has, or it still retains the properties of all linear resistors, meaning it behaves like a linear device. Linear means current and voltage have a linear relationship. If voltage increases, current increases. If voltage decreases, current decreases. So no matter how many resistors are there in that REQ network, it still behaves like a linear resistor. V and I are related by Ohm's law. V equals IR. If you remove R from there, V is directly proportional to I. So if either one of those quantities increase or decrease, the other one will increase or decrease. Anytime anyone has a question, I mean, I take periodic pauses, so have enough time for students to ask questions. But if you have questions in the meantime, simply just raise your hand or just call out. Okay. All right. So how do we derive these? From the law of conservation of energy. Right? KVL, KCL are all based on law of conservation of energy. If you have a source and the source is supplying energy to all the components connected in that at the terminals of that source, all of the energy that is being sent must be consumed or received or absorbed by those resistors. So in this example, we have a current source I. I is going to both these resistors, R1 and R2. We apply Ohm's law. If we apply Ohm's law, the voltage across R1 is V1 or VR1. The voltage across R2 is V2 or VR2. I, of course, is the same current for both resistors. We take it outside. So the total voltage from Ohm's law, V equals IR, where that R indicates is the total resistance, turns out to be R1 plus R2, right? And so Req is simply the sum of all the resistors in that series connection. Mathematically stated, for n number of resistors, Req is the sum of R resistors, and there are n resistors in that series. We simply sum up n equals 1 all the way to n. Sorry, not n, I. Subscript I. Could be any subscript, does not really matter. Okay, simply add up all the n resistors in that network. The series connections, rather straightforward. One other additional important point is that in a series circuit, and we have stated this before, but it bears repeating, current remains the same, or current is the same, not remains. Current is the same, but voltage is divided. And this additional technique that can be used from here, derived based on Ohm's law, is known as voltage division. We won't look at this today, but we'll look at it some other time. All right, does anyone have a question online? Okay. So in a series circuit or a series resistive circuit, current is the same for all resistors, but voltage is divided. So if you are applying one single voltage to 5 series resistors, that single voltage source is going to get divided across each one of those resistors. And the voltage drop is directly proportional to the size of that resistor or the value of that resistor. Okay. All right, let's take a pause. Let me know if you have any questions. Okay. All right, going to parallel, same thing. We apply Ohm's law to determine the total voltage or the, total current that's being split. So we have I total that is flowing through the circuit. Actually, that's not quite correct. I total comes in here and splits in two. So we have two nodes, and so it splits into I1 and I2. You apply KCL at the top, we get I total is I1 plus I2. And then apply Ohm's law, we can describe I1 and I2 in terms of the voltage that's being applied. It's a parallel connection. Because it's a parallel connection, the voltage remains the same. Voltage is the same because it's the same two nodes. However, the current gets divided. Here we have two, so it gets divided into two parts. And the value of those currents depends on the value of the resistors. The smaller the resistor, the higher the current that's flowing through it. If both resistors are the same value, it's divided into two equal parts. And from this principle, we can, and we do have a technique known as current division. So these voltage division and current division principles are derived from Ohm's law. Okay. So your I total is I1 plus I2. Apply Ohm's law, you get V over R1 and V over R2. Voltage is the same, so you take voltage outside and you obtain the total current V equals IR. So REQ turns out to be 1 over R1 plus 1 over R2 in the reciprocal. So what we're doing here is this turns out to be 1 over REQ. So 1 over REQ turns out to be 1 over R1 plus 1 over R2. And hence REQ is the reciprocal of that term. Okay. 1 over REQ is 1 over R1 plus 1 over R2. Hence REQ is the reciprocal. Okay. Any questions about the derivation? This is not something that would be tested or assessed, but this is something that students should understand, how it was derived, how these equations are derived. And we can still apply the same derivation principles to other quantities and other equations. Okay. Right. So what is the advantage of equivalence? I stated this a few minutes ago. If we know the total equivalent resistance between any 2 points, we can treat it as one single resistor. So we can ignore how everything is connected inside that resistive network. We don't really care whether it's series. We don't really care whether it's parallel. All we need to know is between two pairs of terminals, A and B, or C and D, or X and Y, any two pairs of terminals, the total REQ is a specific value. And then between those terminals, we can treat it as one single linear resistor. So if you apply voltage, you can easily calculate the total current that will be available. Or if you apply current, we can calculate the voltage. So in this circuit, in this example, you just want to see REQ between these pairs of terminals. So if you're trying to reduce a circuit down to one single REQ, we always want to adjust everything either in series or in parallel, and then start reducing the circuit branches. So the first thing we can reduce are these two resistors in parallel and these two resistors in series. 10K in parallel with 3K gives us 2.48, and 1 and 1.5 in series gives us 2.5. Okay, so we can reduce those. So let me just draw it out. The next step here is going to be right. So this becomes 2.48K. The ohms is left unstated, just FYI. I usually don't prefer this because I always like to use units and unit prefixes, but never ever leave it unstated, okay? Always have your units correct. This is 2.5, let's say K, and this is still 5.1, right? So the next step after this is to combine it. REQ, still between these 2 points. This becomes 1.68K, and this is 2.48. And now final REQ is one single equivalent resistance, which is 4.16K. And now that we know that the total equivalence of those 5 resistors is 4.16, we can calculate any current, any voltage given the input, right? Simply applying Ohm's law. And this is the technique we use known as series parallel equivalent analysis, where we reduce an entire resistive network down to one single resistor, apply Ohm's law, and then expand the circuit back up again. Okay. So let's take a pause, think over that. Let me know if you have any questions. Okay. All good? Okay, so power. Power is P equals V times I, standard equation. So if we know we are supplying 10 volts, calculate the current, and then calculate power. We'll speak a little bit more about power later on in today's class. But for now, we saw that we can reduce resistors in series and resistors in parallel. What about other kinds of connections? So here's an example where you have a few resistors connected in a slightly different configuration. If we are to find the resistor between any 2 points, we need to analyze the resistors outside of those 2 points and see which ones are in series or parallel. So for instance, if we try to find RBC, RBC is simply the resistor R3, right? And then between B and C, you have R1 and R2. Now, R1 and R2 can be reduced to one single resistance. So this is R1 in parallel with R2. And on the other side, we can reduce R4 and R5 also to one single resistor. And then once that is done, we can say that all 3 resistors left are in parallel, and we can reduce it by applying this equation. Make sense? The reason we can do that is because it's node B and node C. Anything or any components that are connected between those 2 nodes will always be in parallel. Okay, so you start from B and you end up at C. Doesn't matter what branch it is or how many other components are there in that branch, but that entire branch taken together is in parallel with anything else that is connected between B and C. And that's how we look at circuits. Same thing on the bottom side. You start at B and end up at C, and any branch or any component that's connected between B and C will always be in parallel. And this is true for any two nodes in a circuit. Okay, any two nodes. Let's take a pause. Think over that. Let me know if you have questions. Yes. Yep. And so that's B and C. And then if there are no other questions, we'll talk about A, B, and perhaps C, D. Okay. All right. So how about RAB? Those two nodes. What do you think? Let's just copy and okay. So this is A at the top. This is B here. So if it is RAB, first of all, let's find how many single resistors are connected directly between A and B. How many do you see? Which one? Start at A and end up at B. Yep, that's R1. So if I was to find A and B, I only have one single resistor, R1. And the rest of the circuit is to the right. So at this point, I'm not even looking at the rest of the circuit, but the rest of the circuit is in parallel with R1. Okay, so this is A at the top right here. This is B right here. And I have only R1 connected between those two nodes. The rest of the circuit is to the right. But it automatically follows that because the rest of the circuit is connected between A and B, no matter what value the rest of the circuit has, that value will be in parallel with R1 because it's those two nodes. Does that make sense to everyone? Right? Okay, so now look at the farthest end from A and B. What do you see? Actually, there's no resistor here. This is just joint. Okay, that's R1. This is R2. This is R3, R4, and R5. What other resistors can be reduced? Do we have anything else in parallel? Do we have anything in series? What do y'all think? Yes. So 2, 5, and 4 would be in series. The answer is yes and no. So in order, and this is an important concept, in order for two resistors to be in series, they must be connected at only one end. So R4 and R5 are connected at one end. That is correct. So they are in series. However, there should not be more than two connections at that node. So if there is a third or a fourth connection at this node, then they are no longer in series. So R4 and R5 are in series. That still remains the same. That still remains true. But R2 is not in series with R5 because R2, R3, and R5 are joined together. So these are not in series. And I would say these are in series. Okay. All right, let's see. So R4 and R5 can be combined as one resistor. And then let me draw the diagram to the right. Actually, no, let's just do it this way. So from A, I have R2. And then I have R3. And then it's connected to B. And then from this point, I have the series connection of R4 and R5. And that would be the effective resistance between A and B. Let's take a pause. Let me know if you have any questions. Yes. Yes. So point being noted is the reason why R2, R3, and R4, R5 are not in series is because at this node, they have more than two connections. So if any node has more than two connections, they are no longer in series. Okay. Did that make sense? Okay. So RAB probably is not the same, not probably, will not be the same as RBC. And of course, that also depends on the values of the resistors. Now, there is one other thing. If you have resistors connected in sort of a triangle, as we have with A, B, and C, so let's clear demarcation line. Okay, so R1, R2, R3, they are connected sort of a triangle. Actually, not sort of, they are connected in a triangle. Okay. So there is another type of conversion we can perform, and that conversion is known as delta to Y. Delta because it looks like a delta, and Y because it looks like a Y. In words, it is sometimes also stated as delta to Y transform. And there is also Y to delta transform. This is especially useful when we when we study or learn about three-phase circuits. Okay. So here we have three nodes. If you wish to transform these, we can do so. It's A, it's B, it's C. This is R1, R2, R3. We can transform this into a Y circuit. So first, let's draw A, B, and C. And I'm going to move this to the left. Okay. The nodes will still remain the same, A, B, and C. And now we have resistors connected in an inverted Y configuration. Let's call this Rx, Ry, and Rz. Okay. XYZ. Now there are derivations and everything associated with this transform, but we are not going to look at that. I'm going to give you the values directly. How do we find? Well, each one of these is a ratio of the resistances. The ratio becomes like this. You take the three resistors in the delta or the triangle configuration, you put them in the denominator. So Ry is the same. R1 plus R2 plus R3. And Rz is also the same. R1 plus R2 plus R3. Okay. And in the numerators, you're going to put the product of the two resistors that are connected at that node. So Rx is connected to node A. And in the delta config, in the original configuration, we have R1 and R2 connected at node A. So the numerator for Rx is going to have R1 times R2. And similarly, you fill in the numerators for the Ry and Rz. So what do we have for Ry? R1, R3, absolutely. And for the other one, the last one, R2, R3. And so we can, if we ever have a circuit where we have this kind of connection, we can transform it into a delta connection, I mean, from delta to Y. If we do perform this transform on the circuit above, this is what we can do. This is R1. C and D. That's the original circuit. If you transform this into a Y connection, I have A at the top, B on the left, C on the right. Much easier to reduce this circuit. Yes. Now you have, what did we call this? We have Rx, Ry, Rz, let's call this RL, Rm, Rm. Looks more like an E. Let's call it M, N, and O. And now we can see we have two resistors in series on either side. You can reduce those. Those would be in parallel. Reduce that to one single resistor, and then all three would be in series. All right, let's take a pause. Let me know if you have any questions. Did that make sense? Hopefully. Again, we are trying not to overload, so we won't go too in depth at this point or at this point in time. But just know that there are transforms that we can perform. Yes. Let's see, what did I miss? Oh, because R3 will appear in both. So a good question, very good question, is like, how come we have 6 resistors on the right when we only had 4 on the left? The answer to that is because when we're performing the transform, all we need is 3 resistors from a triangle to go to 3 resistors in a Y configuration. So R3 appears in the top and the bottom triangle. And if you wish to practice, you can do so. We already know how to find the REQ from between A and B. Now you can find REQ between A and D. Okay. This is RAD. REQ between RAD. Okay. Right. Okay. Let's go. This. Let's talk about sources and their resistances and what it means to be a practical source versus an ideal one. Okay. So circuit systems are systems that convert electrical energy into some other form of energy. Right? Electrical into optical, thermal, mechanical, any other kind of energy. And so we have sources. This is a voltage source. This is a current source. And then we have resistors, capacitors, and inductors. Those are 3 primary passive components. Ideal resistor is related by Ohm's law, V equals IR. For inductor voltage, V is equal to L di over dt. Capacitor current is C dV over dt. Capacitor and inductors are energy storage devices. So they receive energy, they store it, and they release it back into the circuit at a later point in time. They do not directly oppose the flow of current or the application of voltage, but they do oppose any change in their input quantity. So if you have current being sent into an inductor, if you try to change this current, then the magnetic field or the energy that's stored in the inductor will oppose any change in that input current. Same thing with the capacitor. Capacitor, we apply a voltage, stores the energy. If we try to change this voltage, then the capacitor will oppose any change in that input voltage. And so again, when the quantities change over time, it's going to oppose it. Theoretical analysis is all based on ideal components, but here we'd also like to understand how ideal components could differ from real life components. Okay. So in an ideal component, a voltage source, let's say, is connected to a resistor which has 0 ohm resistance. A voltage source itself does not have any resistance. Ideal voltage source, R is equal to 0. But if R is equal to 0, then we are saying that terminals are short circuited. If R is 0, what is I? Doesn't matter what voltage you apply. If R is 0, what happens to I? It's infinity. Yep, you're right, infinity. So even if you have a very small voltage source, like 0.1 volt, very small battery, very small capacitor, you short circuit its terminals, resistance is equal to 0, current goes to infinity, and power goes to infinity, which is not possible, right? Any source does not have infinite power. Same thing with a current source. In a current source is said to have infinite resistance. Terminals are open. But if terminals are open, that means the voltage, sorry, that means the power is infinite. Okay. So if you have ideal sources, we cannot model them in real life. Okay. We cannot just use them as it is. We have to apply our practical considerations. So ideal sources do not have infinite power capability. Not possible. That's what it means there. All right. So how do we model these? Well, let's say we have an energy source that supplies voltage and current, and we measure the voltage at its terminals. The voltage at its terminals is 12 volts. When no load is connected to its terminals, the current that's coming out or is pulled from the supply is 0, right? 0 amps. Now, if it's 0 amps, sorry, not 0 amps. If nothing is connected, it's 0 amps. Let's say now that we model it as having a resistance R, and this real life source can only supply a max of 100 watts. So equal to or less than 100 watts. No infinite power, limitation on the power. So irrespective of the value of the load, only supply 100 watts. So how can we model such limited power scenario? The limitation in this case is just the power output capabilities, which again, if we go back to the example that I've used before, laptop adapters, chargers, can supply 5 watts, 10 watts, 15, 20, 30, 40, 50 watts. Laptop adapters are bigger, can supply 100 watts, 150, 200, 250 watts. Okay. But if a device tries to pull more power from that adapter, adapters have built-in circuitry, they will shut it down. They say, we can't supply more. Okay. We cannot supply more. All right. So how do we model that real life adapter? Well, we put a resistor in series with that voltage source. So real life power supplies or real life voltage sources will have a resistor in series with the source. This is known as the source resistance or the series source resistance. This is the only way we can actually model a real life power supply. So let's take a pause. Let me know if you have any questions. And there should be a question. Think over what the question could be. Any guesses? The keyword is series. Why series and why not parallel? What if it was in parallel? What is the property of a voltage source? Property of a voltage source is to supply its rated voltage irrespective of what is connected between its two terminals. So if we have a resistor in parallel with the voltage source, no matter what value that resistor has, the voltage source is going to supply that energy. So we cannot accurately model this. We need to have a resistor that is actually consuming some little bit of power inside that source itself. And that is not possible with a parallel resistance. So it must be a series resistor. Okay, so parallel is not possible. The more accurate or the best way to connect, not connect, but model a real life power supply is if you have a voltage source in series with a resistance. Now, typical power supplies, the value of this resistance is very, very low, very close to zero. So here we're just modeling it as 0.36 ohms. Okay, 0.36 ohms. And so if you connect a voltage source, let's say whether it's 10 volts or 12 volts as in this example, and we connect it to a resistor R, a little bit of the current and the voltage is dropped across RS. Okay, so power supplies, the benchtop power supplies that we have are actually designed to compensate for this internal resistance. Okay, RS is the source resistance that is in series, and power supplies are designed to compensate for this resistance. Oh, we're almost at the end. Okay. In order to transfer maximum power, the load resistor must match the series resistance. Again, maximum, in order for maximum power to be transferred from the source to the load, it must match the value of that internal series resistance. We are not talking about efficiency. We're just talking about max power. Okay. The system is capable of delivering certain amount of power. In order for that power to be at a maximum level, meaning if it's rated for 100 watts and we want to transfer 100 watts to the output, then the load resistance must have a value equal to the internal source resistance, RS. This is known as the maximum power transfer theorem. And when we derive it by again applying Ohm's law in that circuit, then maximum power comes out to this value. P is equal to V squared over R. V in this case is Vs. R is a series combination of Rs and RL. Okay, in order for maximum power to be transferred, we set the circuit conditions and calculate Tmax as 1/4 of V squared over R. Okay. Let's see. Next was, I think, current source, but I don't think we have enough time to get into that. All right, so let's see. We'll end class here today and we'll pick up on Monday. Monday quiz will be based on the material we have covered in this week. And so some theoretical questions and maybe one or short problems. Okay. All right. Have a good weekend and I'll see you all on Monday.